4.6 now, we're taking a look at some optimization problems. And that, of course, is going to be problems where we're going to be using calculus to try and find the maximum and the minimum of something, or the smallest or the longest or the shortest or the largest of something. And the way we're going to do that is we're going to get a function that models that certain item that we're looking for, that certain quantity that we're trying to maximize or minimize. And then to find the max or minimum value, as we have learned, we just take the derivative and set it equal to 0 because we know that maxes or mins have to occur at critical values, that is, where the derivative is equal to 0. And so let's start off with some examples here. You can read through the section and look at the examples in this section. I'll let you guys do that. I know you've done it already before you watch this video. And we'll just look at some examples here that will be similar to your homework. Like number 7. We have a farmer with 750 feet of fencing and wants to enclose a rectangular area and divide it into 4 pins with parallel sides facing one of the sides of the rectangle. This is a pretty standard optimization problem. Let's suppose we have ourselves here this fence. So we got this fencing here, and you can put a little detail in if you want, doesn't matter. It's nice green grass maybe that it's sitting on, whatever. So we want to maximize this area here. We're going to have actually 4 sides that are parallel to one of the sides to make, well, actually we're going to have 4 pins, 1, 2, 3, 4 pins. And we want to maximize the area of all 4 pins. In other words, we want to maximize the area of this entire rectangular area. So the first thing you should do is draw a picture. It doesn't have to be a nice picture, just a picture to give you an idea of what it is you're trying to do. And then you need to label sides. You need to label things. We can think of one of these sides here. Let's call this width here, the shorter side, x. And then I'm going to label this entire side up here as y. And so now I can say that the area that I'm trying to maximize is equal to x times y. Now the area, let's go ahead and write out what that is. This is the area to be maximized. The problem with this formula for area right now is, remember that in order to maximize something, we want to take the derivative and set it equal to 0. Well, it's going to be hard to take the derivative of this because we have actually 2 variables here, an x and a y. And we want to be able to take the derivative of a function with only 1 variable. So there's going to be some other information in your problem that's going to allow you to rewrite the function that you want to maximize as a single variable function. In this case, that extra information is the fact that the farmer has 750 square feet, not square feet, linear feet. We have 750 linear feet of fencing to work with. Well, can we make an equation that says that with the variables that we have, x and y? Notice that x is the length of this width right here, and so if we have these other dividers in to make these pins, we also have a width of x here, 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 and here. So we have a total of 5 x's worth of fence. Whatever the length is of x, there's going to be 5 of those. And we have more than one y. We have a y up on top, and we have a y down here. So we have 5 x's plus 2 y lengths has to equal that total amount of fencing of 750. So here, at this point now, we have an equation involving our 2 variables, and now we can solve this equation for one of our 2 variables and substitute it in. So I'm going to go ahead and solve this for y. If you want, you could solve it for x, but I'm going to solve it for y, and that'll get y in terms of x. So I have then that, let's see, if I subtract 2y is equal to 750 minus 5x, I'll divide both sides by 2 to get, what's that going to be, 375 minus 5 halves x. That's what y is equal to. And so what I'm going to do then is I'm going to substitute that into my area function. Remember, my area function was equal to x times y, which I can now say, well, let me write it this way. I'll write it area of x. I can write it as a single variable function now by taking this and putting it in for y, because that's what y is equal to based on the restraint that we had 750 feet of fencing. So the area function now becomes of x times 375 minus 5 halves x, or 375x minus 5 halves x squared when I distribute the x through the quantity. Hey, I got a single variable function now. That means I can take the derivative of this function. Taking the derivative of this function right here gives me 375 minus, what's this going to be, 5x, right? 375 minus 5x. Set that equal to 0. Solve that for x. So 375 is 5x. X then is equal to 75. And the unit on that, of course, is feet. So we're going to need 75 feet of fencing, 75 foot, feet, fencing, whatever. That's what x has to be. What does y have to be? Well, it's easy to figure out. Y is equal to 375 minus 5 halves x. So y is equal to 375 minus 5 halves times 75, which is 375 minus think this is 187.5, which is half of 375, so it leaves us with 187.5. 187.5, and that's feet as well. So that's the unit on this longer side of our rectangular pin, 187.5 feet. So what's the total maximum area? Well, the maximum area is going to be, that's going to be that 75 for x times 187.5 for y, which I think comes out to be 14,062.5, and that's square feet, feet times feet. So that's the maximum area. Now there's some other things that they ask you to do in the book in number 7, so you want to look at those and do those as well, but that's the idea. So again, here's the steps. Draw a picture, label your picture, find a formula for the thing that you're trying to maximize or minimize, get another equation based on the information you have, solve for one of the variables in that equation, substitute that into the formula that you're trying to maximize or minimize so that you get a single variable function. Once you have a single variable function, you can take the derivative of that, set it equal to 0, and you'll see that you have a maximum. How do we know this is a maximum, by the way? Note this area function here. This is a second degree equation. It's a parabola that opens down. So what we have here basically is a function that looks like this, where this is x and this is our area function of x. And you can see that the critical point here is going to be a max. Another way you could check is to take the second derivative, a double prime of x, which is just going to be -5. Since that's negative, concave down means you have a local max sitting on top of that. So there is number 7. Let's look at a couple more examples. Let's go ahead and at least set up number 12. I think once we see a picture of this, you shouldn't have too much trouble with it. Number 12, you have a rectangular storage container with an open top. Okay, so let's go ahead and draw a picture. A rectangular storage container, so it's just going to be like a cube. All right, and it has an open top, so that top part is open. No material on the top is what that means. And the volume is 10 meters cubed, so let's go ahead and write that down. The volume of this thing, we have to have it be 10 cubic meters. All right, the length of the base is twice the width. So let's go ahead and label some things here. Let's label this L, this W, and this H. We're told the length is twice the width. So the length is twice the width, and the height there, H, is, I don't have any information about that. All right, material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. All right, well, let's see. What's the cost going to be equal to? The cost is going to be equal to, this is what we're trying to minimize. We're trying to get the cheapest cost. So we are trying to minimize the cost. So we need a formula for the cost based on our variables here, length, width, and height. And for length, of course, well, what are we going to have here? The cost per square meter for the base. Now the base, the way we have it labeled, if we think this is the base down here, that's the length times the width. And that is $10 per square meter. So it's going to be 10 times that area. Material for the sides is $6 per square meter. So plus 6 times, what's the area for the sides going to be? We have 1, 2, 3, 4 sides, and each of those is a height times a width. So 6 times H times W. Let's see, times, actually 4 of those. 4 HWs will give us the 4 sides there. So this is going to be the total cost of the materials. $10 for the area of the base plus $6 per square meter. So $10 per square meter for times the area of the base, plus $6 per square meter times the area of the sides, and the area of the sides is given by 4 times H times W. Now we want to minimize cost here. So remember what we said. We want to be able to write cost as a single variable function. Well, one thing we can do is we can do a substitution of 2W in for L, like we said, because the length is twice the width. So our cost now becomes 10 times 2W times W, plus 6 times 4, that's 24, times, let's see, 24, we did that multiplication, times H times W. The problem now is that H. We need to get rid of that H and write it in terms of W. Well, volume to the rescue. We are restricted that our volume has to be 10 cubic meters. What's volume equal to? Well, the volume is equal to the length times the width times the height. That has to be 10. Length is the same as 2W, so 2W times W times H is 10. We can solve this now for H. This is just a two-variable equation we can solve for H. So we have W squared H is equal to 5. So H is equal to, looks like 5 over W squared. H is equal to 5 divided by W squared, which we can then substitute in for H right there. And now we can write our cost function C as a function of W. it's equal to 10 times 2 times w times w. That's 20w squared plus 24 times 5 over w squared times w, which is equal to, let's see, 20w squared plus 24 times 5. 5 times 20 is 100. It's going to be 120 over w. 120 over w. Is that right? Okay. So now we want to minimize our cost, so we're going to take the derivative of this thing. We take the derivative, we get, let's see, 40w. Let's see, this is 120 w to the minus 1 is this term right here. So that's going to be a minus 120 w to the minus 2. Minus 120 w to the minus 2. So if we set that equal to 0, let me see if I can get it here. So we've got 40w minus 120 over w squared, and we want to find the minimum of this. So that's going to set that equal to 0, because minimums and maximums occur where the derivative is equal to 0. So let's solve this for w. So 40w is 120 over w squared. So let's see, if I multiply by w squared here, I get 40w cubed is 120. Divide both sides by 40, I get w cubed is 3, looks like. And so I guess that means then that the width is the cube root of 3, and the unit on that is meters. And from that you can find the length and the height as well. So I went a little farther than I planned on that problem. I just wanted to set it up, but we went all the way. That's okay. All right, and I do want to say something about 13 real quick. So let's take a quick glance at that. Whenever you're minimizing or maximizing a distance function, by the way, in that last one, you can verify that this is going to give you a minimum. This critical value of the cube root of 3 is going to give you a minimum by either doing the first derivative test or the second derivative test on your function. So I'll leave that up to you guys to do that. Number 13, you want to find the points on the ellipse, 4x squared plus y squared equals 4, that are furthest away from the point 1, 0. So let's draw a picture here of this real quick. What this ellipse looks like, let me divide everything by 4 here if you don't mind. X squared plus y squared over 4 equals 1. That means on the y-axis we're going to be at 2 and negative 2, and on the x-axis we're going to be at plus or minus 1, because you can think of this as a 1 squared down here. And so here's what our ellipse is going to look like. So we want to find the points that are on the ellipse that are furthest away from the point 1, 0. Well, the point 1, 0 is right here. So there's going to be a couple of points, one or more, that are furthest away from this point. Probably maybe some points up here somewhere. All right, so what you want to do here, you want to maximize distance. You want to maximize distance from 1, 0 to some point x comma y. Now, what does the distance formula say? If I want to take the distance from one point to another, it's the square root of the x values, the difference of those squared, plus the difference of the y values squared. Well, to maximize distance, what you can do is actually you can maximize the square of the distance. So whenever you're trying to maximize or minimize a distance, what you want to do to make things easier is maximize or minimize the square of the distance. If the square of the distance is minimized or maximized, then the distance itself will be minimized or maximized. So we're going to take d squared, which is just going to be x minus 1 quantity squared plus y squared. This is the function that you want to maximize. Now again, you have a constraint on this that you can only use points that are on this ellipse. So what you're going to want to do, I'm going to leave this to you guys, is I'd solve this for y. And you're actually going to have 2 points, because when you solve this for y, you're going to get a plus or a minus when you take the square root of both sides. Solve that for y. Use one with the, well, it doesn't matter actually, because when you put that into your function, in for y right here, the first thing you're going to do is square it. So it doesn't matter if you use the plus or the minus. Alright, but that's going to give you a function, distance function, actually a distance squared function, completely in terms of x. Completely in terms of x. And then, so you get then, from that point, you'll get some distance squared, which will be some function completely of x. It'll be x minus 1 squared plus everything you got when you solved for y squared. So everything that you got here when you solve this for y, you're going to put it in right here. And you're going to take the derivative of that, set it equal to 0, and go from there. Okay, and find your critical points. That'll give you your x value. You get your y value, then you actually get two y values. So you'll probably have something like this and this. So you'll have one single x value. When you take the derivative, you take f prime of x and set it equal to 0. You get a single x value. You get two y values because you'll have a y here that's equal to plus or minus the square root of something. So the positive will be the one up here, and the negative will be the one down here. It may be, I don't know, maybe 0, 2, and 0, negative 2. I'm not sure. Up to you to find out. All right, we'll look at a couple more examples, or set up a couple more at least, in the next video.